Is that okay to start? So yeah, I think this is just a little bit of a summary of, general. We find that the oil and gas industry is just a little bit slow to adapt to new technologies such as machine learning, artificial intelligence. The things are changing, and today's workshop is a great example of it. There are a lot of developments in many areas, of especially around the geophysical applications of machine learning, from the processing, interpretation, and towards kind of in some of the early applications of the acquisition of seismic and non-seismic methods. So it is really helping to improve productivity and efficiency and bottom line. The seismic data enhancement is a specific area that we spend a lot of time on. I work for BP in AGT, and it's a huge part of our daily routine when we try to improve the seismic data to understand the habitat of remaining hydrocarbons, plan the exploration and production wells, monitor field performance. So that improving the seismic data quality, usually from processing, is one of the key problems for us. And you spend millions of dollars on it. But sometimes it achieved at great cost and significant time. Here in Azerbaijan, specifically in BPAGT, but also in other areas where the seismic is being worked at, we're really happy to be on the kind of cutting edge of some of these developments. With recently sort of formed local startup that Izat will talk about, called Waverity. We find that their innovative use of AI to improve seismic data beyond the reach of conventional seismic processing and interpretation has been really useful. We are looking at the technologies that are offered by Waverity. We're working closely trying to understand them, and also seeing how specifically these technologies come from Azerbaijan. Usually you would hear a lot of other areas, but this is probably the first time that this kind of technologically driven startup in using the AI enhancing seismic data has appeared in this country. So we're really happy about that. We're really happy about the people we work with. And this workflow reduces, what could be a month of work and into weeks, and potentially saves millions. So obviously this process required to go through validation. I remember a conversation we had with Paul, and I think we all agreed that the validating what AI is kind of proposed as a solution is quite important. So you need to validate it in areas where there's a lot of wells. And I think this is what Waverity is trying to do. And I think it delivers outstanding results, or at least we believe that. So I think that is a result of collaboration on some data. I think we can see that potentially there are some KPIs that we'll talk about, that, with terms of how the dominant frequencies, sand predictability and data quality improves, signal to noise and so on. So this will try to use that as the KPIs. And the other thing to note is that the collaboration that Waverity had with BP allowed them to use resources of computing centers, and that allowed to kind of enhance the opportunities for the operation. So the impact, I think, is there. We are evaluating that. It offers a large potential for scaling up to potentially more seismic data in other regions beyond here in Azerbaijan, and maybe other applications beyond the seismic. But here we'll talk about the seismic data enhancement. So again, I'm really happy that we work with Izat and the Waverity team. With that, I think we can show an example. So you can show an examples. I hope that was a good introduction to your work.
Thank you, Nazim. Hello, everyone. So over the past few years, the Waverity team and BPAG team, we have been building and testing different network architectures to understand which one, or let's say which combination of domain knowledge and deep learning can provide a real solution to geophysical problems. So it became clear that one of the most important components in this story was the correct representation of data, depending on the target, depending on the problem. So unfortunately, I will not be able to talk the technical details of this work, since these products are already in use in real fields, and I will talk in general terms about the sense. So far, we have completed two products, SIQ and SINA. So SIQ is mainly about enhancement of vertical seismic resolution, and the SINA is provide the improvement of seismic signal to noise ratio. One of the important point is that none of the solution used well data, any well log data. This was the goal initially stopped during the building of the methodology. Thus, this approach is also applicable to fields where there is no well data at all. For example, it can be applicable also for the exploration fields where we have only seismic data. Let me show first results very briefly, results of SIQA. This is original seismic data before the SIQA processing, and you can see the difference in terms of the vertical resolution difference, the after application of SIQA product, SIQA solution. So it's very important to be sure that any of the new events are not some artifact, and I will talk about it in the next slides. The key facts: during all this time, we have applied these products in several of the real fields. These fields have a huge number of wells, which allows to validate the results on different types of field data. So the validation was done on more than 200 wells. More precisely, validation was done on 240 wells with a full data package, including VP, bulk density, gamma ray well logs, and also measured vertical seismic profiles. Additional work was done based on geological interpretation, for example, different top maps, exact value maps, RMS maps, also based on wavelet analysis and spectral analysis. Based on these fields and based on the application, we can say that the signal to noise ratio improved by 48%. So vertical resolution improved by 40%. This average values for all fields where we applied the technique. The dominant frequency across the fields improved from 21 to 32 Hertz. Based on the octave panel analysis, we can say that enhanced seismic contains information after 65 Hertz, and processing time compared with conventional approaches, for example, full waveform inversion, we know that it requires months. The processing of the SIQA requires 5-6 weeks for quite big fields. And considering that the technique behind this methodology is deep learning based on image to image, and the main time required for the simulation takes only during the training process, but it's quite quick during the application of the ready model. So the second product is SINA. Let me show the results. So we have image before the processing and after. So on the left side, you can see the estimated noise based on substitution between the original seismic data and processed based on SINA data. At these stages, we have only two products, SIQ and SINA, but in addition to improving the existing products, we are currently working on other, for example, automatic seismic interpretation, 4D seismic inversion, hybrid FWI. Hybrid FWI is our next product when we try to build a physics-based deep learning technology for quick and accurate modeling of full waveform inversion. And the last one is AVO classification. During the all technical procedure when we passed, we can say that it's very important to have a true and right representation of initial data. Sometimes it's very important to represent the data not in time domain, but in frequency domain, and even in frequency or time domain. Considering the differences between neural networks, we can say that for the image to image translation, UNet showed the better results considering fully customized architecture and the fully customized matrices, and analysis not only based on accuracy of the performance of the architecture, but it's very important to analyze the results based on real true KPIs as a part of post-processing. So I think during next 6-7 months, we will have the next product, hybrid FWI, and we will have the chance to validate it on different PPHD fields. So it was a very brief information about the products mentioned by Nazim. Thank you for your time. If you have any questions, please ask.
Yeah, and that would be fair to say this is the other products are in development.
Yes.
We don't have it. Yeah. And then the other thing about the the other two products that are there in the line, I think we're being validated across many other areas. So right now this is done in two fields, as you mentioned, but this is probably a wider application in other areas. Will help to kind of make it more universal. It was an anonymous question, right? So I can take that one. What would you believe that these AI-driven workflows will replace? That's a good question. I think people are thinking about it. What we can say, we see that at least some of the data enhancement workflows, like the noise removal and the spectral shaping and various other post-processing flows in this specific kind of techniques could potentially enhance, replace, and at least equal products. So I think the developments there are quite, at least that's what we're seeing. For the whole data processing, you would obviously need to go back and do it in processing level. At any stage of the processing, I think AI is applicable. But here, this is more of image enhancement, so that's probably post-processing. And I think maybe you can take a second question. Is that from Olivier?
Yes, it's about artifacts. Yes, yes, we did. The main validation during this part was done based on the synthetic data extracted, built based on the VP and density from the logs, and also measured vertical seismic profile. So based on this validation, we didn't observe any new events that is not tracked in log data or in VSP data at high frequencies. For example, at the frequencies more than 45 hertz. So we can say that we didn't observe any artifact during the improvement of vertical resolution of seismic data. Or another thing is during the denoising algorithm, we didn't remove any true events, true seismic events. So it mainly removes only the different types of noises, considering noise, colored noise, Gaussian noise, random noise. Sometimes it able to remove structural and orientational noises, but not real events.
There are three questions here in how many domains you products allow to show seismic data. I'm not sure what this means. Maybe you can say that.
Domain, if it means that time or frequency domain, or for example CWT map, we can show in different domains, of course, because there's no difference in terms of the flexibility and difference from the real data. So the representation can be done based on time domain, frequency domain, or time frequency domain. So the next question for AVO classification, which kind of ML you used? So we're using customized unit with different types of new matrices. For example, one of them is multi-structural similarity index measure to cover not only the average value of the objective function, but also local values, and to save the topological and geometrical part of the data. So generally it's unit. For users, small number of files and seismic data is enough. I didn't get, is it a question?
Well, I can type it, I guess, yeah.
Is it a pre-trained network that can be applied to any data set? Actually, even if we don't use any well information, but to generate the data for the training process, we extract some important features in different time domains from the real seismic data. And based on the extracted features, we generate synthetic data to cover not only the frequency spectrum, but also different types of wavelets and different types of geometry of the field. By geometry, I mean the shape of the layers. And also we add the information about the structure of faults or set of the faults. Before, we cannot apply the pre-trained model on different fields. We need to train the model for each field again and again. But we have the option to improve the methodology based on previous experiences, previous fields where we applied the technique.
Excuse me, could I ask a question?
Yes.
The results you showed looks good, but really I didn't see any keynote presentation like this because you didn't show any details about your work. Like you presented only like 3 slides. So I really want to know more about this. For example, this result, how do you get this? You just explained that you need to retrain the network for every single field. But how do you generate the training data sets for each field data set?
Okay, yes, unfortunately, cannot share deep details, but I can say that when we try to apply the technique on new field, first of all, we need to extract some features. For example, it's different variation of wavelets across the field, statistical wavelets, especially not based on the well information. So extraction of statistical wavelets is estimation of signal to noise ratio. Also structures of faults, for example, is single faults or intersecting faults, a set of the faults. So there are some features that we are extracting in time domain and then in frequency domain. That information is for generation of synthetic data to build the synthetic data very close to the real seismic data. Another question, how we are using the output data, how we generate the output data, because it's supervised learning and we need to have a labeled data. So I think in very short term, we have pre-processing technique that able to say which time of boost we need to generate over the existing extracted wavelets. And based on this boost, we are generating with the same features of real seismic data, we are generating more data with more high frequency band without touching the low frequency part. So based on some sensitivity analysis, we can say which time of setup is the best one to generate the output data, to have the labeled data set.
Okay, thank you.
Recovering the frequencies with deep shows got target some. So yes, we at the beginning we had the problem that some even not 65 hertz but more than 45 hertz we had the artifacts, but it depends on how you build your KPIs at the end of the network. For example, how you choose the matrices. It's one of the important parameter to eliminate possible artifacts in the results. So at this stage, considering all these details, we have no artifacts. So as you see, based on 200 wells, more than 200 wells, we validated, our internal team and BPHD team validated the results. So again, it's very important to have VSP data because VSP data provides high frequency information. And sometimes when we think that some events are artifacts, if we see this event in the VSP data, so we can say that the new event is not artifact based on only VSP data, because only information that can be used for the events after 45 hertz. This is a very good question. Do you trial version of your softwares? At this stage, we have only algorithms. It's not software. It's not user friendly. But after when we will have several types of products, we think to build a software as a package of AI and seismic. What key features allows reducing the processing time? So we didn't do nothing special to reduce. The only thing we did is optimization of the network, reduction of the complexity of the network without losing the accuracy of the results. But when we compare processing weeks versus months, I mean that it requires weeks versus the conventional approaches, which requires months of simulation time.
Yeah, I think maybe the better definition is that, when you do processing and then the post-processing conditioning and spectral shaping, right? Noise removal at any stage, that takes time. That probably you'll talk about the months. Here, this is very quick. So that's where it's not really the processing from field tapes, right? We're not doing that. We're enhancing the data image, typical kind of post-processing steps. Yeah.
And last question, I think, do you work with large data sets? Yes, we are generating large data sets based on the initial seismic data because we have no any limitation. The number of data sets depends on if we want to cover all possible scenarios of geological fields, we need to create big data set to cover all of them. So we are using actually large data sets, but it doesn't depend on size of the field because we try to generate the synthetic data based on the true data and it doesn't depend on the size of the initial seismic data. Are you using the manual interpretation of horizons faults as a desired output? Unfortunately, yes, because this is the input in terms of the horizons and faults before the training process is extracted based on the manual part. But after the processing, we can see we have better tracking. For example, based on one point of the seismic data, we can build better tracking of the horizon. But for the training, yes, unfortunately, we are using the manual interpretation. The last question, yes, we didn't change anything when we tried the network on different fields. So the architecture and the so the fully customized architecture is universal to apply for any field. Thank you.
So the next presentation is from Lucas, and he will talk about using machine learning for mineral exploration, target selection. So let's give the turn to Lucas. Welcome.
I'm Lucas, and I'm a participant of a great team with members from the Federal University of Goiás, Brasil Minérios, and the Colorado School of Mines. We developed an application of machine learning in vermiculite exploration using airborne geophysical data in central Brazil. So to begin with, vermiculite is an industrial mineral generated by hydrothermal and weathering processes in ultramafic intrusions. The main objective of this project was to generate predictive prospective maps using machine learning on airborne magnetometry and radiometry. The first step was to select deposits in the area as models and study their signatures, their geophysical signatures. Then we ran the algorithm using data from those model deposits to find new prospective spots and refining parameters for the algorithm when necessary. So finally, we selected some of those prospective spots from a final predictive map as targets. The study area was selected based on the possibly fertile geological area around existing deposits. And here we can see the flight lines of the survey and the existing deposits as the polygons. As those deposits discovery has relied on geophysical data aligned to geological mapping, it is very common that they are cut by the lines, as we can see here. So a machine learning approach was suggested to this kind of mineralization to try finding less obvious deposits. So the geophysical data itself consists in an airborne survey that in Brazil is of public domain, which makes it a very cheap tool, and it comprises of magnetometry and radiometry with flight lines spaced by 500 meters with a 100 meters flight height in a north-south direction. The main products that we used in this project are the total gradient, which is the same as the analytic signal, the total count, equivalent potassium, thorium, and uranium, and the digital elevation model. The mineralization expected signature is the same as the host rock, which in our case is ultramafic rocks, and would represent high magnetic values and low radiometric counts, as we can see here in a strip log from a drill hole from one of the model deposits. We can see how the vermiculite grade is related to higher magnetic susceptibility and lower radiometric counts. But of course, this also depends on weathering, composition, and many other factors. So having that in mind, we selected 4 different deposits as models comprising a wide range of mineralization signatures. And to validate those signatures, we performed petrophysical measurements on some drill holes, as we can see in one of the examples here. And although the model deposits signatures are very different from the surrounding rocks, which are not ultramafic, they can also be well separated between each other. Morro Pelado has a classical signature with the highest total gradient and the lowest radiometry count. Jatobá also has a high total gradient, but higher radiometry than the classical type. São João 6 has lower total gradient and also higher radiometry than the classical type, so it would be the further from the classical type. And Segredo has the lowest total gradient, but a radiometry that is similar to the classical. We used a random forest algorithm, inputting a total of about 190,000 points, from which only about 500 are located in deposits, and they are related to the geophysical features in those points are geographically related to selected classes. We generated 28 different predictive maps with the values that I mentioned before as features and background, and all the model deposit as classes. And then from this starting point here, some alternatives for classes, features, and training settings were thought, aiming to reach better results. The most important alternative was to reduce the most we could the geophysics interpolation cell size to increase the amount of points inside the deposit. So the smaller but yet reliable cell size was of 50 meters. We also gradually increased the number of training trees in the algorithm, and the line between under and overfitting was around 1,000 trees. Then we ran some tests without elevation values, so removing the digital elevation model and other features related to elevation that we came across, which improved the overall results. The deposits don't seem to have a topography related mineralization, and some tests without a total gradient to highlight radiometry anomalies. And finally, we changed the classification input, first using points inside all existing deposits, not only the models, ending with a background or deposit classification, only 2 classes instead of 5, and then classifying them, all deposits, by their size, ending with these following classes: 0 for background, 1 to the smaller, and 3 to the bigger deposits. We recognized 3 best predictive maps from all the 28. In all of them, we used a 50-meter cell size, no elevation value, and 1,000 trees. The main difference are the classes. Map 18 is classified using the 4 model deposits. Map 22 uses points from all deposits and no magnetic value, helping finding not so magnetic ultramafic bodies, which we know occur in the area. And map 25 also uses all deposits, but with the size classification. All maps were continuously visually validated by checking if they indicated the existing deposits as targets. But for those best ones, we ran a validation based on drill hole data. For map 18, we achieved a matching rate of 53%. Map 22 has an 85% matching rate, and map 25 has a 91% matching rate. So considering that the drill holes are concentrated, are located inside the deposits, this is expected because the later maps 22 and 25 use more points from different deposits, so it would represent a higher matching rate. And of course, this validation only considers results inside deposits, and matching rates for background are considerably higher. So to take advantage of all those maps in individual parts, we generated a final predictive map by summing their results using a specific value for possible targets of each map, generating a product with 0 representing the background and each value representing a combination of 1 or more maps possible targets, as we can see in the table. Then the points were ranked by importance. If it occurs only in map 22, it is low. If it occurs in 18 or 25 or one of them and 22, it is medium. If it occurs in 25 and 18, it is of high importance, and when it occurs in all 3, of course, it is very high. So finally, the targets were selected if they have at least medium importance and or their geophysical signature is recognizable, aligned with previous knowledge in the area. Rank 1 targets include the most probable to be fertile, combining all those factors I just mentioned. In rank 2 are targets with high or very high importance. In rank 3 anything below medium importance that has a recognizable signature. So even if it wasn't indicated by the algorithm, if it has a recognizable signature, it would be in rank 3 targets. And in rank 4, targets that have already been investigated before, but still might have some unrevealed potential. So in total, we selected 82 targets distributed like we can see here. So now, finally, the final map and the targets in the right, we can see here the very high importance points in red, and the selected targets are the white polygons. So we can see how they are coincident with the higher total gradient values that we can see at left. For radiometry, it might not be as obvious, but it is as well possible to see how targets reside in areas with low overall counts. Here we can better see the distribution of those targets and their ranking associated with the geophysics in the north area. You can see how red and near other deposits targets are ranked as 1, and so in the central area as well, but as I said, rank 4 would be for targets that have been somehow investigated, but might have potential. In the southwest area, which don't have any existing deposits, but also might have potential. And now the conclusions, we managed to generate the final predictive map with possible targets ranked by importance, and then select final targets and rank them. We identified that regional data aligned to machine learning can be a useful and cheap tool, especially in Brazil for mineral exploration. And we also saw that combining more than one product of machine learning with different approaches can be a good solution to achieve better results. And we recognize the most important features and classifications for our case using machine learning. And they can be transposed for other ultramafic hosted cases, for example, and even further than that, tested and checked if they can be used. So this is our work. Thank you for your attention, your time. I'm open to any questions.
Okay, thank you, Lucas. May I ask a question?
Yeah, sure.
Could you go back to the figures where you have the target detection? So all these targets verified. Did you verify the targets that you detected? Are they all the true targets or
to verify in field?
Yeah, because you detect a lot of targets here, right?
Yeah.
So are they all correct, or maybe there are some fake ones?
No, we verified some of them, and there are a lot, and this area is very large, so we couldn't finish verifying all of them. We also ranked them to do this with more assertivity. So the first field project, we verified 11 of them, and we could see in field that at least 2 were positive. And in Brazil, we have a lot of soil above rock. So sometimes those deposits, they don't outcrop. So we would need a drilling program to verify the targets. And this is something we didn't do yet, but from the 11 we checked in field, at least 2 are positive.
Okay.
Answering Olivia, we try to use the magnetic depth in previous projects, but with visual, like with geologists interpreting the data. For this approach with machine learning generating the results, we didn't use it yet, but it's a very possible and indicated way to advance in this project. And the advantages, now answering Sidali, are that when we use the classical methods, sometimes we we also did this and generated targets with the classical methods. And then we combined some of this knowledge from the classical methods with the response of machine learning, and then came with those targets here. But sometimes we might lose something in the way that we can see with classical methods that the machine learning might see. So as it uses a lot of data, this would be an advantage to give a higher importance to the data itself and not only what we see. And we validated the interpretation by the field checking and comparing the interpretation with what we see in the geophysical figures to see exactly if there is a recognizable geophysical signature in those spots that we see here in the map. So there are some like yellow, which would be a medium importance target from the final map that we did not select, and there are some yellow spots that we did select. So this was the process of validating as well. And after validating, we found that here the spots that are as targets are validated and the others are not. So I'm not sure if I answered the question, but this is a very practical approach.
Okay, Luca, thank you very much for your presentation, and thank you for your for answering the questions. We'll move to the next presentation from Amo, and the topic is about multiple parameter inversion of magnetic animals over 2D deeping dike by using extreme gradient boosting methods.
Hello everyone, my name is S.H. Bronson Aimon. I am currently doing my master in applied geophysics at Indian Institute of Technology in the School of Mines, Dunbar. So today I'll be presenting my work, as you can see in the slide, which is on multi-parameter inversion for 2D deeping dike anomalies using XGBoost. A 2D dike model is an important geological structure which is used for interpretation of various magnetic anomalies. They are used in oil and gas industries to model the basement topography, and also they are used in mineral exploration to model the ore bodies like iron and sulfide ores as they intrude in the form of a dike. For this reason, various methods have been proposed, like the Euler deconvolution, the Gauss-Newton method, Hilbert transform spectral analysis technique for interpreting a dike anomaly. But the problem with these methods are that they are highly subjective and they require the initial model parameters to be very close to the true parameter. So in this study, we try to implement a fast and efficient inversion algorithm based on XGBoost, which can tackle these problems. So XGBoost, or extreme gradient boosting, is a tree-based method, which is an implementation of gradient boosting technique. They can be used for both classification and regression problems, and they are mainly designed to give a single output. But in this, however, in this case, we try to use this algorithm to make it predict multiple outputs. So as you can see in equation 1, this is the modeling equation that we have used. Here, K denote the amplitude coefficient, theta is the index angle, and Z is the depth to the top of the dike, D is the half width, X naught is the origin. So these are the model parameters that we have selected. And for using this model equation, the assumptions that we have made, the strike of the dike is infinite, the extent of the dike is infinite, and the upper surface of the dike is horizontal, and also the magnetization is uniform, and there is no presence of remnant magnetization. So in this study, we have done both the forward problem and the inverse problem. So in the forward problem, what we have done is that we have taken the model parameters and then feed into the model equation, then generate the synthetic data set. And in the inverse problem, we have used this magnetic anomaly curve and then get get back the model parameters. And here you can see the flow chart of the methodology that we have followed. First, we take the model parameters, feed into the forward modeling equation, generate a synthetic data set, then split the data set into a training set and a testing set. Then using this training set, we determine the optimum hyperparameters, train the algorithm, and using the testing data set, we evaluate the model performance. Then we generate a new example and predict the model parameters using this train algorithm. So for the synthetic data generation, we have taken the particular search range as shown in this table, and we have used a uniform random sampler. So it will take random numbers within this search range, and then during each iteration, it will take a random numbers in this search range, and we use that to input in the model equation and generate the synthetic data. Then using this synthetic data, the models are hyper parameter tuned and trained using that synthetic data. So in this table, you can see the default setting, that is the default hyperparameters of the XGBoost, and the hyperparameters that we selected for tuning. Here, n estimators is the number of trees, max depth is the maximum depth of each tree, and the learning rate step size is also for step size, and the rec lambda is give the L1 regularization, rec lambda give the L2 regularization, and these are the optimum value that we have obtained. And in this bar plot, you can see the R2 score and the root mean absolute error and the mean absolute error of the trained algorithm. As you can see, the R2 score is quite high, and the error root mean square error and the mean absolute error is quite low. So after that, we generate a synthetic Dike anomaly using these model parameters, and we also add Gaussian noise, a 5% Gaussian noise and a 10% Gaussian noise in this synthetic Dike anomaly to test the effect of the noise in our method. And these are the results that we have obtained. So as you can see, as the noise increases, in the case of 5% noise, the RMS error is actually decreasing. So like this can be interpreted as our method or XGBoost algorithm is able to handle less noise. But as you increase the noise to 10%, then the model performance start to decrease. And in the below figure, you can see the plot between the predicted anomaly and the true anomaly, and we can see that they are fitting quite well. The predicted anomaly is fitting the true anomaly quite well. And in order to test the interference effect of nearby structures in the Dike anomaly, we have generated a composite anomaly curve. So here we have taken a 2D dipping dike with model parameters of K 1500 nanometer, depth of 9 meter, half width of 4 meter, and the origin of 0 meter, and a thin dike and a nearby thin dike structure of amplitude coefficient 2500 nanometer and origin having 40 meter and depth of 4 meter. And here you can see the composite anomaly curve of these two bodies. So we input this anomaly curve into our machine learning algorithms, and these are the results that we have obtained. So in this case, you can see that the predicted anomaly curve is fitting the observed anomaly curve very well, and the predicted values using our current method is close to the true values, and we can say that it is performing better than the previous study also. So as you can see in the amplitude coefficient case and also the depth case, which is closer to the true values using the our algorithm. Then we have taken two field examples. One is from magnetite iron deposit in China. The profile length in this case is 222.5 meter, and it is digitized with a sampling interval of 10 meter. And these are the results that we have obtained. So in this case, we can see that the predicted result are close to and more or less close to the previous study result and also the drilling data. And on the above figure on the right side corner, you can see that the predicted anomaly plot and the true anomaly plot are fitting quite well. And in the below figure, you can see the predicted value plot, cross plot between the predicted value and the observed value, which have a good fit with R2 score of 0.88. And we have taken another field examples from Pima copper deposit in Arizona, USA, which have a profile length of 750 meter. This magnetic data profile is digitized at an interval of 15 meter, and these are the results results that we have obtained. So as you can see, the predicted result using our current method is close to the previous study result. On the right figure, you can see that the predicted anomaly curve and the true anomaly curve are fitting quite well. And on the below figure, you can see the plot of the predicted value and observed value, which have a good fit with an R2 score of 0.99. For the conclusion, I would like to say that the main advantage of our method is that it can handle a wide range of input starting model and then produce satisfactory results even if the starting models are far away from the solution. It can handle a small Gaussian noise, and it is extremely fast once the algorithm has been trained. And the drawback of this method is that, or this algorithm is that it requires large training examples and it has a large training time. And these are some of the reference that I have taken. And lastly, I would like to thank Dr. G. Srinivasa Rao, Dr. P.K. Khan, and the Department of Applied Geophysics. Thank you.
Thank you, G. So do we have any questions? I think we have one here from Mal Adam. Why do you use this algorithm especially, and what's the benefits of it, and at which case in geophysical exploration should you use it?
I've used this algorithm because currently XGBoost is, like as we have seen, it is a go-to method in many of the major machine learning competitions, and it has won a lot of Kaggle competition too. And it has also been successfully applied in seismic facies interpretation. Wanted to test this on the interpreting the dike anomaly.
Thank you. And we have another question from Said Ali. How do you check the artifacts of machine learning? He's speaking about causative sources, I think.
Okay. No, unfortunately, I haven't. I haven't checked that.
Yeah, the other question is similar to the previous one. He speaks about how you validate the machine learning interpretation.
I've shown in this figure, I think, the field examples, and there are previous studies that have been conducted using different methods, and there are also drilling result that has been is available. My model is predicting close to that value, so that is that is how I validate my results.
Thank you, Shi, for your interesting presentation. To move to our next speaker, who is Clara. She'll give us a presentation about k-means clustering on seismic and electrical resistivity data for geological facies identification. Let's welcome Clara.
Hello. Thank you for the introduction. I'll present an application of k-mean clustering based on seismic and resistivity data acquired on catchment in France, near Strasbourg, to identify geological facies. So this work is done in collaboration with French researchers, Norman Lespard and Jean-François Girard, and is also part of an M1 research project that we do at the University of the French Azerbaijani University, which I'm from, with the students Kamal Beramov and Alizada. So I'll talk about an application to groundwater. So groundwater, there is a growing use today and growing vulnerability to change and human activities. So there is a need to build sustainable water management, and for that, geoscientists will assess the resources, extent, availability, and quality, mainly defining the reservoir parameters. So it works quite well, but when we have hard work reservoir, then we have preferential pathways, strong heterogeneity, and spatial variability of these reservoir parameters, which makes for a very complex environment. So how do we identify the hydrogeological zone where you will have the water regarding where it's only weathering but no water? So geophysics has been applied a lot to define these different areas using different methods to image the subsurface and give the different properties. In hydrogeological application, we use a lot of methods together, the idea being to have as many information as we can get from the surface, from logging as well. So you often the data that we have like direct relationship together, they have different sensitivities and resolution. So it's hard to interpret them together or do joint inversion. And in the last few years, machine learning have been applied more and more to improve joint interpretation and present more objective subsurface data. So I will present an application of that. So we work on data that come from the Strangbar catchment. So it's in the Vosges mountain in France. So it's a granitic catchment that present different degree of hydrothermal alteration. So we have a lot of weathering. And there's two questions that are asked while studying this catchment is the hydrological patterns and the solid transport through the critical zone. So critical zone is defined from the top of the canopy to the healthy rock. So you have the exchange between ground, air, and water. But here I will show only subsurface. This observatory actually has been studied since 1986. There is a lot of data and diverse methods that have been applied. I will present today the P-wave velocity and electrical resistivity measurements that we assume are related to the geological facies. Previous studies on catchment. I don't know if you see my, actually, I'm not in full mode, sorry. Do you see my mouse? Not
Yes.
Sure. So the previous studies show vertical alteration due to weathering, so soil, saprolite, then the rock that is highly fractured until the mostly have rock basement. But also it has shown that the southern slope of the catchment is a lot less weathered than the northern part where we have past alteration due to past hydrothermal circulation. So we expect to have a lot more circulation of fluids in the northern part. And there is also a variation at the central alluvial part where the weathering profile is 20-meter thick with high permeability and high water content. So the idea of the test that we did, that I present today, is to try to see if P-wave velocities and your electrical resistivity contain this information, and with machine learning classification, can we detect them? So the data in themselves, so we use 6 ERT profiles and 7 seismic profiles that were done next to each other, although not at the same time. So we have them all over the catchment, so we can see the difference between northern and southern sloping. I just want to note that the coordinates for the ERT are not very precise because the data were done by different people at different time. There is some uncertainty in our data. The letter represent the ERT lines in red, and S plus number are seismic profile. So if we look at the inversion tomographies of seismic and ERT, we can see that we find a 3-layer medium with resistivity that decrease with depth, while P-wave velocity increase with depth. Colors are reversed. But mainly we can see, even with just the inversion, that we have a difference between the location of the lines. So here, for example, ERT, we have a very thick, high resistive layer at the surface, whereas when located on the southern slope, whereas for the central part, we have the same resistivity, but a lot thinner. And when we get to the northern slope, this thin layer is a lot less resistant. For the seismic, however, there is some variation along the line of this thickness, but mainly we can see a difference for the line that is close to the river, where we can even define 4 layers. So we can see that ERT and seismic sensitive to the weathering state of the granite, and more so for ERT. So let's see if the machine learning find this information as well. So we use, as in terms of machine learning, the k-mean clustering. So it's unsupervised classification. So the k-mean will group into clusters the attributes, the data, based on their similarity, meaning that the kind of the same properties. So we use 2 attributes here, the centered values of the logarithm of resistivity and the centered reduced value of the logarithm of the P-wave velocity. So k-mean clustering will assign a k-random centroid. So k meaning the number of clusters you want to make. So for example, if you want to make 2 clusters, you will choose a random point in all of these and call them centuries. Then you calculate the equivalent distance between each of the data points to these centuries, and you associate the data point to the nearest, making clusters like that. Once your clusters are formed, then the centroids are recalculated to make it more central to the cluster. And since centroids are reallocated, you have to redo the whole process, and it's repeated until the repositioning of the centroids is over, meaning that the algorithm converge and you estimate that the clusters are optimal. So this is what we did. So one important part in k-mean clustering is choosing how many clusters we have to choose. And we use here, there's different methods. We use here silhouette score. So it's a widely used and effective method that has been proven many times to work. So here, the measure how similar the data point is to its own cluster compared to the other ones, and the high value indicates that the data is in the right cluster. You make a mean of that, and you get an optimal value for all the clusters, all the data. Here we define that the number of clusters, the best one is k equals 4. And on the right, you can see so that's the score for all the data points in each of the clusters. And when you go above the line of this mean value, it means that you estimate that it is a good value of cluster for all the data. However, usually the shape is the same or should look the same, meaning that you have the same amount of data in each of the clusters. It's not the case here, but it's still the optimal value that we get. So with 4 clusters, we have divided our data rather classically. So with the cluster 1, low resistivity, high seismicity, cluster 2, low seismicity, high resistivity, and these 2 together, where you have a medium resistivity, high velocity, and low resistivity, medium velocity. We want to look at them first in terms of depth distribution. We can see that cluster 1 and 2 are mainly dependent on depth, meaning that cluster 2 is localized mostly at the surface. So all these data points will be located at the surface, whereas all these ones will be located towards that, all lines together. And but for the other 2 clusters, there is a lot of overlap, meaning that depth might not be the only influencing parameter. And this is why we look at also the where the cluster are located in a catchment. So, and we see that there is an influence by the rotation of the points in a catchment. So when we look at cluster 0, so the purple one, after 10-meter depth, we can see that it is mostly located on the southern slope. So the highest values, resistivity, and not the highest values of velocity and the rest of resistivity. And the cluster 3, yellow, is confined to the first 10 meter, but also will be located to the axis of the valley and the northern slope. So if we look line by line, we can see that this cluster 0, the purple one, is a lot thicker on the northern slope lines. And when we get closer to the Strangbar River, so it's like the blue line is representing the river, we can see that these purple points tends to disappear most of the time. So towards the river, there is no, this type of value we do not find anymore. For cluster 3, the yellow part, we can see here that the southern slope, there is a few of them that have been allocated here, but otherwise it's mostly on the valley axis and a little on the northern slope. So there's clearly an influence by both the position in space and depth. With 4 cluster, we highlight 2 influencing parameters, the depth and the spatial localization. We have 2 cluster 1 and 2 that depend mostly on depth, whereas cluster 0 and 3 are also influenced by the variation, the position of the line in a catchment. So we were able, with this simple test, to confirm that machine learning, that both ERT and seismic are sensible to the variation of the weather state, and that the clustering can find it. However, we saw that 2 attributes might be too limited to define clearly the clusters, as we have some points that might not be really well allocated. So when choosing the number of clusters So for example, the silhouette method didn't give very high value, and the fact that we had different shapes between the cluster meant that maybe we do not have the optimal number. When looking at depth only, we can see a lot of overlap, meaning that yes, it's not, maybe we should take it into account in the attributes. The two students did a parallel study where they applied the k-means line by line. So here I took all the data together, all the lines, and I applied the k-means, but they showed that by looking at the different lines separately, the distribution is of the clustering is really different where is the line in the catchment. So we'll continue working on that. So work like line, and we introduce more attributes like the altitude, depth, distance to the river. We might even take into account the geological information. And of course, we can use other classification methods because k-mean is not the only one that exists. Thank you.
Thank you for your nice presentation. We have one question here. So are you using the raw VB and resistivity values, or you're extracting some features for classification?
So we did the inversion here, this one. So we have the two inversion, and we took the values from the cells of each of the models and we put them together. So we use the inverted values, not the raw ones. Okay. And there is another uncertainty here because I did not do, other colleagues from France did the inversion and seismic and ERT, so I don't know which parameter they use for the inversion. So that might also change the results.
Thank you, Clara, for your interesting presentation. I'd like to introduce our next speaker. So we will have Lex. He's speaking about automated assessment of slope stability. This is an application of machine learning to ERT monitoring data.
So my name is Felix Kiszkurna. I'm going to show to you the results of my project on automated assessment of slope stability. I have applied machine learning methods to automatically interpret the ERT monitoring data. First, I will give you a brief introduction and motivation. Then I will discuss synthetic data I have used for my experiment. Then I will explain to you my experiment setup, show the most important results, summarize them, draw some conclusions from them, and make some suggestions for future investigation of this problem. The main goal of my project was to test capability of machine learning algorithms to automatize interpretation of ERT profiles obtained as a way to monitor landslide sites. This goal is important because landslides are an event that is widely occurring in the whole world, as you can see from the map on this slide. They can cause significant loss of human lives and have a huge economical impact on the communities they affect. So it would be beneficial to those who are impacted by this threat to develop easily and cheaply deployable methods to automatically monitor those potentially dangerous sites so that the communities can be given an early enough warning to limit the damage. ERT is commonly used to monitor such areas, and in order to test the capabilities of machine learning algorithms and not the quality of measurement or of ERT for a specific site. Most of the experiments and tests were run on synthetic data so that it's a fully controlled environment. As you can see from the figures, the geometry was selected to be big enough so that the boundary conditions have no effect on actual survey area. On the ERT survey, the survey was done with dipole setup with 44 electrodes and 64 meters. First, the survey was simulated using forward modeling, and the data obtained from survey were inverted. Those two steps were done using PyGimli Python package, and as the goal of this study is to test machine learning capabilities, not to investigate the best way of inverting ERT data. All profiles have been inverted in the same way with the same setup and the same parameters. This had additional advantage of introducing some profiles that were not inverted as good as they could have been, so that it could have been tested how machine learning algorithms will deal with this kind of problematic data as well. So in total, there were 84 profiles used. 42 of them were normal and 42 of them were inverted. For this study, normal profile is the one in which the low resistivity layer is on top on the high resistivity layer. You can see an example of such a profile in the upper illustration in this slide. The inverted one is the opposite of it, and you can see an example of it in the lower illustration. There were 3 resistivity contrasts used in those data sets, and 13 different interface steps. First step of the experiment workflow was to split data sets between training and prediction profiles. As I was testing many different combinations of pre-processing steps and features, the split between training and prediction profiles was always done in exactly the same way to avoid some random influence of specific profile split. In the training phase, all the training profiles were put together and given to the clusters and classifiers at the same time. They were pre-processed using different pre-processing methods. They are listed in the box on the right upper part of this slide. For each classifier and cluster separately, there was performed a hyperparameter grid search in order to allow each of them to perform up to their best capabilities. Next, there was the training phase. The training phase was evaluated using the accuracy metrics, and after the training, each of prediction profiles have been performed prediction by those pre-trained clusters and classifiers. The same pre-processing steps were applied to both training and prediction profiles. Next, evaluation metrics were applied to the results delivered by machine learning algorithms. The most simple one that was used is the accuracy score. It just gives you a number of how many, what fraction of points in the given data set were assigned the expected class. This, however, is not the most appropriate way of evaluating the results in this study, as the goal is not to assign all the points correctly. It is beneficial to assign all of them correctly to the main question, but the main question is to identify the depth of the interface between those two layers in the profile. And in some cases, especially for clusters, it is common that the best or very good results are achieved even when the classes are assigned incorrectly. So a very low accuracy score can occur at the same profile at which interface detection was very successful. Interface detection accuracy is not a metric that should be absolutely trusted in all cases. Therefore, additionally, feature important and confusion metrics were used as well. These figures gives you an overview of all results achieved in different tests by classifiers. Each test had a different combination of pre-processing steps and features that were given to the classifiers. It was done in such a way in order to identify impact of all of those steps and features on the final result. As you can see, the achieved range of accuracies between different experiments is quite wide, which allows to make a conclusion that pre-processing has a very, very strong impact on the final results. With the same algorithms and the same input data, different pre-processing steps could make a difference from basically useless and completely inaccurate prediction to one that is very satisfying and potentially could be sufficient for many practical applications. The same thing can be said about clusters. The accuracy ranges are a bit bigger here because of the problem with incorrect class assignment, but still there are many experiments, so the many pre-processing step configurations in which very good and very satisfying results have been achieved. In these slides, you can see an example of one of the best predictions performed by classifiers. The left-hand side figure compares true depth of the interface with predicted depth. The black line in the middle of this figure is a reference line. The points that are exactly on it are the profiles for which the depth of the interface have been predicted perfectly. Generally, each point is one profile that was performed prediction on with one algorithm, and generally can be said that the closer the points are to the reference line, the better the prediction result was. In the range of depth between 2 to around 12 meters, there is a slight tendency to overestimate depth of the interface, which changes to underestimation between 12 and 15th meter. What is interesting is that there is a very high overlap between different algorithms. Apart from a couple of outliers, all algorithms have basically delivered exactly the same answer. Right-hand side figure shows the detailed results achieved for one of the profiles. As you can see from the middle row and in the right-hand side column, the classes have been assigned almost perfectly, and the subfigure above it shows that the interface have been identified as good as it could have been considering the quality of the input data. Very similar can be said for clusters. However, there are a couple of differences. The change from overestimation to underestimation is not as clear as in classifiers, and the overlap between two algorithms that were tested is not as good as it was for classifiers. It will require a further investigation to identify why one of them performs better than the other in certain situations. And as you can see from the right figure, the best result has been achieved with incorrect class assignment, which does not mean that this result should be mistrusted or rejected, but it would require some additional verification steps before it can be considered as trustworthy. So generally, with the summary can be said that with the good quality of input data, most of the machine learning methods can accurately detect interfaces. There were some differences discovered between the preference for pre-processing steps between clusters and classifiers, but there were as well some similarities. In the next phase of the study, the best trained classifiers clusters that performed best in the synthetic data phase were used to test them on real data. As you can see from those two figures, especially from the right-hand side column in the upper row in both of them, in real data, both clusters and classifiers have successfully identified two interfaces instead of one, which is a very optimistic result because all the synthetic data profiles that were used to train them included only one and entirely horizontal interface, which is a clear difference to the real profiles where there are two interfaces and a slope. This allows to make a very careful conclusion that it may not be that important to train the clusters and classifiers on a wide range of different geometries and spatial characteristics of the profiles, and it may be sufficient to train them on fairly simple ones. However, it has been discovered as well that the generalization in terms of resistivity contrast between layers is way harder, and clusters and classifiers perform great when they are faced with real data that has the same or similar resistivity contrast as the training data, but they perform quite poorly when new resistivity contrast is introduced. This limitation is definitely something that will have to be considered for practical application, but generally this study has shown some proofs that training on synthetic data and predicting on a real one could be for many sites a sufficiently accurate methodology. The impact of the training data is quite noticeable, but even with fairly simple pre-processing steps, the final result can be greatly improved. However, achieving a generalization can be challenging. It is easy for geometry and spatial variability of the profiles, but it is significantly harder for the resistivity contrast. So there are still a lot of aspects of this application that needs more investigation, like for example this problem with incorrect class assignment with clusters. It has to be investigated to what extent it is actually giving us unreliable data and in what situation it can be relied on. There were only few real data with more complex profiles tested, so further investigation is required in the future as well. But generally, I think this application of machine learning methods is very promising. Thank you very much for your attention, and now I would like to answer any of your questions.
Thank you for your presentation. Seems like that we don't have any questions. 13 minutes break. Afterwards, we'll start our next session for this day. It's about machine learning for facies and fault identification of non-seismic methods. Thank you, Flakes, and I'd like to thank all the speakers of sessions 1.
So, hi everyone again. Welcome back. We'll be able to begin the second part of the day, second session. The session will be about machine learning for facies and fault identification, application of non-seismic methods. And we'll begin the session with a presentation from Wanjun, Lithology identification via domain.
Hello everyone, I am Haining Liu from China University of Petroleum. Today, I will introduce something about geophysics with artificial intelligence and highlight the work related to the lithology identification via domain adaptation. I will start my presentation by sharing the introduction, formulation, our work, experimental analysis, and conclusions, and further work. First, it is one of the strategic directions of oil and gas in national energy security to predict oil and gas content by using data analysis and artificial intelligence methods. The main concern here is to interpret the logs intuitively speaking. It is to build a classification to predict and interpret the lithology according to the logs. Although a large number of studies have been conducted in this area, most of them have been carried out under the assumption of independent and identical distribution. In fact, due to the differences in sedimentary environments, logging device, and drilling mass, the same lithology might have different logging characteristics into different wells or different formations. As shown in the figure, TSNE visualization of data distribution for well A and well B, green, yellow, and green indict mudstone, sandstone, and dolomite, respectively. Those and boxes indicate the data from well A and well B, respectively. A significant distribution discrepancy exhibits between the training dataset and testing dataset. So IID doesn't hold anymore. As shown in the following two figures, the non-IID problem causes an accuracy decrease in interpreting logs from another wells by the trained class official. Therefore, there is a great risk of accuracy loss when directly applying the trained model to an uninterpreted well. In view of the above different distribution of source and target domain, neither supervised nor semi-supervised classification methods can handle this situation. So, some pre-processing, such as domain adaptation in machine learning, should be done before interpretation. Firstly, we formulate the geophysical logging calibration problem and give statistical explanation. Then, we present the derivation of our method and illustrate its application in logs calibration. Finally, we conduct massive experiments in 3 wells and 6 tasks to show the effectiveness and interpretability for multiple wells. In the logs interpretation problem, the lithofacies corresponding to the instance xi of the total K0 types is denoted by this function. The discrepancies of probability distributions between 2 domains can be seen as the discrepancies of 2 giant distributions. Although, in general, the condition probability distributions are shared across domains. Therefore, the problem tends to tackle the inequality of marginal probability distributions. In order to improve the performance in the case of probability discrepancy, we propose a calibration method to learn a calibrating function f and let this. We first give some preliminaries, including ELM and MMD. ELM can be used to address classification and regression problems, which is proposed by J.B. Huang. Its model training is efficient compared with some traditional learning algorithms. Meantime, completing regression and multi-class classification tasks effectively. MMD is generally used to mean the similarity between two probability distributions of the source domain and the target domain instance. The way to establish a lithology identification model while domain adaptation is illustrated in the figure. A sample, which is composed of the loading values and a certain depth, is a vector. The circle, triangles, and stars in the figure mean the samples, the classes of which are indicated by different colors. It is observed that the conditional distributions of source domain and target domain are very different. For the case that geophysical logs calibration aims to adjust the logs of one value to align it with another. To achieve this goal, we propose a method by combining ELM and MMD. We introduce the random mapping used in ELM to our method. The instance X is mapped to high-dimensional feature space by H. A transform matrix bit combined with MMD operating to each mapped instance is used to reduce the distribution discrepancy. In order to maintain the physical meanings of the alignment feature, the regularization term of source domain maintenance is introduced in the calibration of bit. In addition, we add a complexity measure term. Eventually, we abandon the solution. The FE scores for each lithology are shown in the figures. It is easy to find that SO usually overfits to the milestone so that its FE score might be high on some task. Our method eliminates the distribution discrepancy in the 6 tasks, so the classification after logs calibration could perform well on each lithology. Take the migration from A while A to while B as an example. The graph exhibits a visualization of while A logs in the task A to B before and after calibration. It shows that each log in source domain has a slight change. Most microscopic characteristics are preserved. Some are weakened due to the low-pass filtering function of the regularization. The graph exhibits the visualization of while B logs and the corresponding predicted lithologies in the task A to B before and after calibration. Some logs have a great change. The predictions are significantly improved by our method, observing areas A and B, such as R25. In areas C and D, the calibrated logs change greatly, but it keeps the basic variation trend of the original logs, taking A to B and A to C as examples. It can be seen from the tables that the mean of each log in the aligned target domain and source domain are almost the same as those in the original source domain. This indicates that the means are aligned unilaterally. In order to see the result of our method more intuitively, we give the frequency distribution custom of logs. It is easy to find that the aligned logs have the similar distribution to the source domain. Here shows the distribution of AC and COND counts. Here shows the distribution of JR and R1225 logs. In conclusions, we formulated the geophysical logs calibration problem and gave its statistical explanation, exhibited an interpretable method of lithology identification, via domain adaptation. We could align the logs from one well to another without losing the physical meanings. Massive experiments showed the effectiveness and interpretability from multiple wells. It is an unsupervised feature domain adaptation method, so it doesn't rely on any labels from cores. For the work, actually, the source domain labels could be used to pre-train model and output some pre-undo labels for the target domain, such that we can obtain a conditional MMD instead of the marginal MMD used in the paper. With the conditional MMD, the conditional probability distribution of both domains could be aligned, which might have a better calibration effect than the current work. Thanks for listening.
If anyone has any questions, please put them in the Q&A box. Okay, there's a question in the chat. The question is, this calibration will keep the high frequency content of the signal, correct? They're asking about your calibration. They are asking, does your calibration keep the high frequency content of the signal? Could you type in the chat then the answer to Sid's question? The high frequency information might be lost slightly. You regard it as denoising, okay? Since we added reconstruction part in the net, we can use it for synthetic seismogram generation or not. We can use it to denoise the seismic data. Okay, I see no additional questions. So thank you, Heng Yan Liu.
Thank you.
Yes, thank you. So we'll go on to our next talk, machine learning application to identify rock lithotype versus facies. Presenting will be Fidan Astanzada and Ulvia Abdulkarimova.
Hello, good day. Thank you very much for the opportunity to present the result of the work that we are doing as a research project in the French Azerbaijan University. My name is Fidan Aslanzadeh, and today, together with Ulvia Abdulkarimova, we would like to present you the results of our ongoing research dedicated to the identification of the lithotypes in the reservoir rocks and opportunity to define with this the types of the facies that are present in the reservoir. I will present the first part, and Ulvia will continue with the second part of the presentation with the testing of the different machine learning methods. We will go through the introduction, some objectives of the research that we outline for beneficial results, then some methodology part will describe you why we took this or another method of the machine learning, and the data session, so you can understand how we extracted the reliable amount of the data that might be put into the model for the simulation. Then we go through the result discussion and the future perspective. First of all, let me briefly introduce you to the research area. The research area is located in the Caspian Sea in the northern hemisphere of the Europe, and as a part of the research, we took the western South Caspian Basin, that is offshore region of the Azerbaijan. The major hydrocarbon production units are buried in that region. As you might see, this area is holding a lot of them saturated with oil and gas structures that are produced now, and there are a lot of the data exist together with the seismic or well-logged data together with the core data. And in our research, we took a chance to make a simulation on the well-logged data. And a brief historical geological history introduction also. So our research is based on the reservoir rock, and the reservoir rocks are deposited in the South Caspian region by the delivering with the Paleo-current river system. And this river system was deposited a huge amount of the very very nice sand reservoirs. And however, the deposition environment was quite frequent. And as you might see here, the examples of the delta river distribution as a pattern. However, together with this, with the high frequency plate fluctuation of the climate, the environment changed rapidly from the river dominating environment to the lacustrine dominating environment and delta dominated environment together from the proximal and distal part. So that was a tricky question to understand how fast this environment might change in one framework of the reservoir. And a bit of the reservoir introduction for you is this column that is representing the Early deposit. It's actually the time when these reservoir rocks were deposited, and the Early types period deposits are subdivided in Azerbaijan region of the South Caspian Basin into parts, lower and upper part. And basically, you might see here an legend, so a very sand-prone reservoirs, and especially in an offshore region. And the part of our research is taken from the upper section of the product of the Early Pliocene deposit, the reservoir, which is the reservoir that is very promising for the hydrocarbon situation. Okay, so let's move to the objectives. The first task was of course to define the presence of different lithotypes. Then we defined the different facies types that exist in reservoir, and we used machine learning method to classify the lithotypes and facies from the well-logged data. That helped us in a theory to define the particular facies types, and based on that we can define the alternation, and based on the lithology alternation we can define the facies. Okay, and manually it was done before. So how it was done, we were having the log data, maybe a potential log, or it may become array log, and we estimated the volume of the shales log, and out of the volume of the shales log we could predict the boundary limits for the clustering of the sand-prone or clay-prone thicknesses. And based on the alternation or the shape of the progradation or aggradation of on this log section, together with the frequency of the lithology changes, we could define the facies. So that was done manually, and when you have logs around 50 in one field, it may be a very tricky question to work on it. And 3 machine learning methods were chosen to perform this analysis. The first method is the k-nearest neighborhood method, that is allowing you to define an algorithm that is solving the regression and in the nearest point. And the second method is the decision tree. This tool is also used for the classification, and it's having a flow chart like and tree like structure. And the third method is the random forest method, that is algorithm can help us to classify and output classes selected by the decision tree method. And the data session, the area which is located offshore, has a square kilometer around 33 square kilometer, and the total number of the wells existing in our data is 163. And also that we chose 13 wells that we were continuing doing the machine learning research. So the next part will be presented by Ulviam. Ulviam, the floor is yours.
So as Fidan mentioned, our objective is to use machine learning methods to classify lithotypes and facies from well-logged data. And particularly, we are interested in training our data on one well and testing it on different wells. And here, first, we can see the distribution of facies types in different wells. And clearly, we can see that there is a great variation in the different wells depending on which facies types are present. So for our work, for now, we used well 5 as the training well, and we tested our results on the different wells. And next, then we can see here the distribution of lithotypes in different wells. So here we present the box plots for 8 of the wells. And again, we can similarly see that in well 5, we have all the 5 types of lithotypes. So therefore, we also used this well as a training well in order to test the results in the different wells. So here, actually in this presentation, we present the preliminary results of our work. So here we show the 3 machine learning methods, KNN, random forest, and decision tree. And in the table, we can see the precision, the accuracy of our model for the different wells. And we can clearly see that our results are looking very good, especially decision-tree performed the best, and whereas KNN was slightly, and random forest were slightly poorer, but overall the results are still very good. And this is mainly because there is a good correlation between the lithotypes and the volume of shale. And for our model, the main parameters that we used were the volume of shale and the depth. And here we see the results of facies identification using 3 different machine learning methods. And here the results are obviously poorer, though KNN seems to return better results than the other 2 machine learning methods. And mainly the results are poorer because there is a large variation in the facies types between different wells, and it really depends on the training data. And as our future perspective, we plan to choose our training data more carefully in order to be able to obtain better results. Okay, and another objective of our work is to look into the connection between lithotypes and facies and determine different facies types from the alterations of different lithotypes. So here we present the histograms for 3 of the wells, and we see some kind of a pattern between different facies groups and different lithotypes. And however, this is also needs further investigation and to see if it is possible to classify facies from the alteration of different lithotypes. So overall, we showed that we obtain better results to classify in classification of lithotypes, whereas with facies, the classification was not very satisfying. And again, this was due to the selection of the training data. And so in the future, we plan to use maybe 2 or more well-log data to build our training data set, and as well as try different methods such as maybe deep learning methods to see if we can improve our results in the case of classification of facies types by training on lithotype alterations. That was all. If you have any questions.
Thank you guys for your attention.
Thank you, both of you. Do anyone have any questions? You can post it in the Q&A box.
Data from one well, well 5, for training is enough?
Yeah, it was actually, it worked very well for the case of lithotypes. Fortunately for the facies classification, the result was not very satisfying. That's why I think maybe we need to choose our training set more carefully so that there is a kind of even distribution of different types.
You suggest using deep learning. Could
Yes,
you explain more?
Yes, actually, it is just an idea of testing it. We have not tried it, so I cannot say more about it, but maybe we can try to see if it can give us better results.
Thank you. Have you tried to combine somehow results of 2 or 3 methods together?
Combining 2 or 3 methods together? No, we haven't tried.
Machine learning versus SOM, which is better?
Sorry, what is SOM again? Yeah, I'm not sure about the question.
SOM equals self-organizing map.
I don't know. I haven't. I'm not very familiar with the self-organizing map.
Maybe we'll bring that topic up at our discussion at the end of today. We can talk about one versus the other. Any additional questions?
Following up on the question for the training data set, you choose only one well and you suggest maybe using another well. Why do you choose only one?
Yes, for now, one well worked very well for the classification of lithotypes. And that's why we thought for facies classification to also try one well. Actually, I did try 2 wells, combination of 2 wells as well. The results were only improved just slightly. So that's why maybe I'm thinking maybe we need more than 2 wells or to, to build our training data. Maybe that would help, but that will be tried in the future.
Okay.
Can I comment also on this? We choose one well because this one well presented all the lithotypes and all the facies that we could train our model on.
Yeah.
Not every well is holding the whole complete picture of the facies and lithotypes.
Okay, we have some additional questions. One is in the chat. A KNN, Cronin network, self-organizing map, and unsupervised vector quantizer are very similar algorithms. All right, so that wasn't a question, that was a statement. And again, we can work this into our group discussion at the end. Thank you.
Some questions on the question answer thread. How
Mhm.
many logs did you use? Well, in total, we had 13 logs and we presented only 8 of them. But for training the data, as I mentioned, we used only 1 log. And how do you QC your classification of your training? Well, do you please elaborate on this?
Okay, so you said that you have a numbers of wells and you did the training on one well.
Yes.
So we assume that the clusters, you will have different clusters in the well.
Yes.
So how do you know that these clusters are geologically meaningful? Do you have core data to make sure that you have the specific cluster which is correlated to a specific rock type?
Ulrika, would you like to reply or I can comment on it?
Yeah, you can comment on it, I think.
Okay, the thing is the major cluster that we may rely on is the thickness of the sandstone that are presenting the reservoir, the channel sandstone. So that was the major cluster we were operating with. And afterwards, the consequent alternation of the fine sandstones with the clays that were presenting the floodplain position.
Okay, so I have one more question here. So you said that you did the training in one well and you applied this training model at the rest of the wells, right?
Yes.
On the 13 wells, right?
Okay, so how about the heterogeneity of the reservoir? I understand this is a sand reservoir, so I do not assume to be a very heterogeneous reservoir, but sometimes you find that one well that you have thick sand units that shales out or becomes a little bit silty in other intervals. So how about the heterogeneity when you apply the heterogeneity or the lateral heterogeneity across all the wells?
Okay, so the heterogeneity was part of the research that was done before, and especially if we speak about this horizon. However, the heterogeneity in this research were not connected, meaning that the next step is to do the mapping of our results, which is not done yet.
Okay, thank you.
Thank you.
Which logs do you use as input?
All right, yeah.
And the volume of shale.
So SP log, spontaneous potential, we can take the gamma ray log and estimated volume of the shale's value, VCH log.
Thank you.
Thank you.
Okay, thank you. I guess we can move on to the next presenter, Krishan Suddenly. I pronounce it right. Effects of training data sets, proportioning in ENN and DL analysis for petrophysical characterization.
Hello everyone. I will do a presentation on a recent research we did on effects of training data set proportioning in ANN and deep learning analysis for petrophysical characterization of a fractured granite basement reservoir. This research was funded by Vietnam Petroleum Institute. This is the content of the presentation. First of all, I will do a brief introduction about ANNs and deep learning. Then we'll move on to the methodology of the research. After that, we will look at the results and some important observations. Then we'll go to the conclusion. Artificial intelligence has become a very popular topic in recent times among researchers in reservoir engineering, petrophysics, and geophysics. So when we are talking about artificial intelligence, we cannot neglect the term machine learning. So machine learning is a subset of artificial intelligence that uses techniques which enable machines to use experience to improve at certain tasks. So two popular methods used in machine learning are ANN and deep learning. So first of all, we'll look at basic introduction about artificial neural networks and deep learning. I am pretty sure you are very much familiar with this, but as an introduction, I will explain about some basic ideas about ANN and deep learning. So the concept of artificial neural network was put forward by McClock and Pitts back in 1943. So ANNs were inspired by the function of the neurons in a biological brain. So figure 2 shows the structure of a neuron in the brain. So what is happening here basically is that impulses or signals from outside are captured from the neuron as inputs, and they are sent through to an axon to give an output. A similar concept is used in artificial neural networks. So in an artificial neural network architecture, there is an input layer, hidden layer, and output layer. So when it comes to deep learning, I would like to define it as an upgraded version of artificial neural network. So architecture of a deep learning has multiple hidden layers. So in a traditional artificial neural network, there is only one hidden layer. In deep learning, there are multiple hidden layers, which make the architecture deep. Deep learning has the ability to map out very complex relationships between inputs and outputs. So let's move on to the data division, which is a focal point of our study. So when we are talking about the dataset plays an important role when predicting an output in a machine learning model. So the output can be affected by the number of data points we use, how noisy the dataset is, and based on the missing data in the dataset, all these can affect the output. However, in this study, we are focusing on how the proportioning of the dataset affects the output. So training dataset is divided into three portions, as we all know: training, validation, and testing. Training set is basically used to train the model. Validation set is used as a sample of data to provide an unbiased evaluation of a model fit for the training dataset while tuning model hyperparameters. So test dataset acts as an independent dataset which provides an unbiased evaluation of a final model fit. So keeping all these in mind, I believe that you have a slight understanding about the objective or the main objective of the research. So the main objective is to understand the effects of training dataset proportioning of training to validation to testing in ANN and deep learning analysis for petrophysical characterization of a fractured granite basement reservoir in Coulomb Basin, Vietnam. So let's look at the overall methodology of our research. So first stage was acquiring data. So in this stage, we obtained well-log data. Well-log data was used to identify the lithological zones, and also it was used as input data when constructing artificial neural network and deep learning models. So after acquiring data, as I mentioned before, zones were identified in the lithology. After that, fracture porosity was calculated by a conventional method suggested by Eliquidi and Tiap back in 1998. These values were used as target data. So now we have input data and target data. So using those data, we constructed our artificial neural network and deep learning models for different training, validation, and testing data proportions. So for each model, we determine coefficient of determination or R-squared value. So based on that, optimum models were identified. So a real-world data set was introduced to the models to predict fracture porosity. After obtaining results, these results were compared. So this is the figure 7 shows the study area of our research, which is Coulomb Basin. Coulomb Basin is situated in the south of Vietnam. So our team, geophysicists in our team, identified 3 zones in the lithology. So in the first zone, it was weathered granite. Second zone, it was tight granite. And third zone, it was fractured granite. So when we were preparing the training data set, as I mentioned before, target data were obtained by using an equation suggested by Eliquidi and Tiap. So equation 3 shows the equation we used to calculate the fracture porosity. So unknown terms of these equations were substituted using equation 1 and 2. So input data used when developing the ANN model were well-log data. 8 types of well-log data were used: gamma ray, deep resistivity, shallow resistivity, interval transit time, bulk density, neutron porosity, photoelectric factor, and caliper logs were used. So again, target data were the fracture porosity values calculated by the equation I mentioned before. So in this case, we used 5 data proportionings to identify or investigate the effects of data proportioning on the output. So in the first instance, we used training to validation to testing data proportioning of 40 to 30 to 30. In the second instance, it was 50 to 25 to 25. In the third instance, we used 60 to 20 to 20. In the fourth instance, it was 70 to 15 to 15. And finally, we used data proportioning of 80 to 15 to 15. These are the results we obtained. We have summarized the data results we obtained. So in the first column, you can see the variation of different data proportioning. And for weathered zone, tight zone, and fractured zone, we have tabulated the predicted fracture porosity values for ANN and deep learning, and coefficient of determination values of ANN and deep learning have also been tabulated. And next, we will look at some important and some interesting observations we can draw based on the results we obtain. The first one is artificial neural network and deep learning analysis was successful successful, and predictions of fracture porosity were quite good for all the data proportioning ratios for each type of weathered, tight, and fracture zones. So if you look at the R-squared value, which is often used to compare the performances of a machine learning model, is quite high. So generally in machine learning, if the R-squared value is higher than 0.7, it is considered as a healthy model. So in this research, we found that R-squared value for both ANN and deep learning for all three zones were higher than 0.75, which shows all the models performed well for the training, validation, testing ratios we used in this research. Ratio of 80 to 10 to 10 gave the best results for both artificial neural network and deep learning. So if you look at again the table which shows the results, you can see the ratio of 80 to 10 to 10 gave the highest coefficient of determination values for artificial neural network and deep learning models. So in the weathered zone for 80 to 10 to 10, ANN gave 0.86, which is a very healthy value. Deep learning gave 0.9, and for tight zone, ANN gave 0.9. Deep learning gave 0.94, which is very high. And in the fractured zone, ANN gave 0.81, and deep learning gave 0.89. Another interesting observation was deep learning results obtained are better than those by ANN. Again, if we go back to our tabulated results, we can see the coefficient of determination value of deep learning is always higher than artificial neural network. So for all three zones, weathered, tight, and fractured, R-squared values obtained for every training, validation, and testing ratios, it was higher than ANN. So finally, another observation we had was the accuracy of the prediction improved with increasing proportion of training data in both ANN and DL models. So this is an approximate observation, I have to say. If you look at when the training portion of the training, validation, testing set increases along the column, overall R-squared value also increases. So this is also an interesting observation. So to conclude, in this study, effects of different data proportioning of training, validation, and testing on fracture porosity prediction using ANN and DL models for investigation. So data proportioning 80 to 10 to 10 provided the best fracture porosity values for both ANN and DL models for Coulomb base in Vietnam. So predictions from DL models showed a higher accuracy than the ANN models for all data proportioning for fracture porosity prediction for Coulomb base in Vietnam. So these are the conclusions that we drew at the end of the research, and also for the future. As a thought, I would like to mention, so we can say that data proportioning can be done using many combinations. So in this study, we focused on similar number of data points for both validation and testing datasets. So for further study, it can be done for different number of data points for validation and testing datasets. So that is the end of the presentation. Thank you.
In case of absence of a disparate output or small desired output, what do you suggest as a solution?
As long as we have the well-logged data, we can calculate the desired output using the equation. So in this case, we did not have much of a problem when obtaining the desired output, since we used the equation suggested by Eliquidi and Tian. Case of like, if I go beyond what I have presented today, if you have a problem in finding some sort of input data, you can use a software like MATLAB. They provide options to some sort of do an estimation on missing data.
Okay. The first question is R2 computed on the test data set or on all data sets?
It was done to all data sets.
Thank you. What about overfitting? Did you see effects of the proportioning on the degree of overfitting?
So basically, the intention of using a validation data set is to avoid overfitting. So in this case, so if you look at the proportion of 80 to 10 to 10, it gave the best result. So we cannot come to a concrete conclusion based on that. However, if you only look at the data set, if you look at the results we obtained in this study, we can say that when the proportioning of 80 to 10 to 10 was used, we had the least overfitting.
Thank you. Our next question, did you test less log curves as the input? It seems that you have used all 8 log curves as the input.
Yeah, this is a good question. I did not check for less log curves. However, we used all log curves based on a previous study we did. We did a study on Coulomb basin to predict fracture porosity using ANN and deep learning. So in that, we found that all 8 log curves have an effect on the output. Therefore, we decided to use all 8 log curves.
Thank you. In case of the absence of a disread output or small desired output, what you suggest as a solution for lithofacies classification in shale gas reservoirs, what do you suggest as a solution as a network or as a network?
The thing is, in shale gas, if you look at the petrophysical properties, it can be very complex to characterize. So deep learning can be a great solution in that case, because deep learning has the ability to map out very complex relationships between input bits and output. So if you are interested in that, I highly suggest use deep learning when classifying or even characterizing shale gas reservoirs.
Okay, thank you. There's another question back in the Q&A. In that case, your results can be explained by overfitting your data and also why DL is performing better than ANN.
Your R-squared table, it was computed on the training data, on the validation data, and on the test data, right?
Yes.
In that case, if you increase the training set and you are overfitting your data, you will always get a better result. And the larger your network, the more degrees of freedom, the better your result. So if I would go for 99% or even 100% training set, I would get the best R-squared per definition. So the valid test should be on the test data set, the data that has never been seen by the model during training and validation. That's the one that should determine whether your proportion is better or not.
Yeah, I can agree with you on that. So in this case, you are saying, so in...
I'm saying that your table suggests that you are overfitting your data. Because the larger your increase of your training data set, you go from 40 to 50 until 80 eventually, you always see an increase in the R-squared. And that is contributed by the training set, because the training will always go down and down and down because you're overfitting at some point.
So even if the number of data points we are using is higher, still we are thinking the overfitting will happen, like this phenomenon will occur?
I think overfitting it always happens with these large neural networks. And the bigger you make your network, so you put in more degrees of freedom by including more hidden layers, the better the network will actually be able to emulate and recognize the examples in the training set. So you will get eventually with enough degrees of freedom, so enough nodes that can do this prediction, you will always get a perfect fit.
Yeah.
But that doesn't say that you are actually doing a better prediction. The prediction is tested on your test data set. And that is what I think you should have put in your table, the R-squared of the test data set.
That's a good point.
So I think we should move to a group discussion, which I think we were kind of progressing to anyway. I'm going to give everybody the ability to talk, unmute themselves, and we can have a discussion about any number of things, such as SOM versus some of these other methods. Clara, do you have anything?
No, I was with you. We can move on to the discussion. And does anyone have experience comparing ML versus SOM?
Maybe I can come back to this supervised versus unsupervised, because I was a bit surprised by the use of KNN versus random forest and decision trees, because decision trees and random forests are supervised approaches, and the KNN, at least in my opinion, is a clustering technique, is an unsupervised approach. So I wonder if the term KNN was used correctly here, or whether it could have been a vector quantizer, a supervised vector quantizer.
Sidoli has his hand up. Go ahead, and we're already unmuted, so go ahead.
Okay, thank you very much, Laurie. So thank you, sir, for your nice presentation. Just I have a question about deep learning. So running deep learning sometimes taking a long time and the overfitting problem. So So the deep learning exactly in geophysics, we can use it in which problem? In which problem we can use for example, for the facies classification, for the Petrophysical parameter estimation, and which type of reservoir? Is it in complex reservoirs only, or we can use it for conventional reservoirs? This is the question.
Yeah, can I answer this?
Sure.
I think deep learning has a place in conventional reservoirs, unconventional reservoirs, in basically any type of problems that we tackle. And there are very good examples already of different applications, both in seismic processing and seismic interpretation. And I think that the key always is whether you can actually capture the problem in terms of a problem that can be given to a machine learning algorithm to train on. That means that you need to create examples for this deep learning algorithm to work on. And you can think of examples like fault prediction, where you have simulated a number of fault seismic models, or you have created models with different types of faults, and then you created synthetic seismograms for this. And that application has been quite successful already. In terms of reservoir characterization, there are good examples of deep learning algorithms that have been trained on synthetic data. What we have seen today were examples where we had only real well data to train on. And then, of course, you are very quickly getting into this overfitting problem, because the networks are extremely large. You have very large amounts of degrees of freedom, and that means that a network can basically recognize the individual examples of your training sets. And then you get into problems, because then you're not predicting, but you're just recognizing that individual example. And to circumvent that, you can simulate data. That can be done with simulating pseudo wells, for instance. It's very easy to create from one or a couple of wells a whole range of simulated wells with all kind of variations that you expect to find in the setting that you are working with, and then use these type of pseudo wells to actually train your machine learning models. So you can go from synthetic pseudo wells to synthetic seismic, and then you can train a machine learning model to go back from the synthetic seismic to the model parameters, like what is the net to gross, what is the saturation, what is the lithology, what are the seismic or the facies that I can expect to find in these type of models. These are applications that work, and they work not only for plastics but also for carbonates and for different settings. So I do believe there's a lot of good applications already that are useful at the moment for being applied, and that really give value to your data. And these are just two examples. There's many more that you can think of, and I think there will be many more coming in the near future, because this is still very new technology that is developing very fast at the moment.
Thank you very much. So I have another question, please. How to avoid the problem of overfitting in deep learning? The number of idle layers, is it very important in the to avoid overfitting problem, or no?
Yeah, it's extremely important in my opinion, and I think there are two basic ways to avoid this. Obviously, you always have to look at your performance, your training curves. So whilst you are training, you are looking at the errors on the training set, but also on your validation set. And at some point, if one of them, the validation set, is going up, then you are overfitting. So then it means that you are continuing the error on the training set is going down, but you are losing the predictive power. And what you can do about that is two things. Either you create more examples, so you do more interpretations, or you do more simulations. And secondly, you can do what is called data augmentation. And that means that you are taking your examples and you are modifying them artificially. Like, for instance, if I have an interpretation of faults, here I have input seismic and I have output the fault prediction, then I can also flip my fault my seismic image, and I can flip then also the fault interpretation, and then I have 2 examples instead of 1, and I could add noise to it, and I could change the polarity, or I could rotate things. So all these things are called data augmentation, and with that you can increase the number of examples. That's what people do when they don't have enough examples. But yeah, that's the way to go. So data augmentation and creating more examples, but always check what is going on during training.
Okay, so the number of hidden layers in the deep learning, is it important, or is there any rule to choose for the choice of the number of hidden layers for the deep learning?
I think deep learning, there are different definitions. And if you look at the networks that we have just seen, which is just more of these hidden layers, and you just increase the network, then yeah, that is a form of deep learning. But I think the more interesting forms of deep learning are these new algorithms which are based on convolutional neural networks. These are the UNets, the GANs, the ResNets. These are networks that have been developed in research, and there are all kind of variations on them, but the best ones are already available in commercial applications, and you can just pick these up, and these can do amazing things without you actually tuning the number of layers and that kind of stuff. Especially the UNet is at the moment the most popular network in geophysical applications, because it transforms an image into another image, like a seismic image into a fault prediction image. And this model has to be proven to be very powerful in solving a number of problems. If you're not into research, then I would just go for these type of models that have been proven already, rather than playing with the number of parameters and let that be done by the researchers.
Krishan, if you would.
Hello, Paul. We discussed about that trade-in to validation to testing ratio a few minutes ago. So yep. I want to correct something. I think I understood your question wrongly. So I did the R-squared value calculation based on factor porosity predictions when an independent data set was introduced to the system. I think in that case, R-squared, we can come to the conclusion that 80 to 10 ratio was better at predicting factor porosity.
So that was on the validation set, what we saw in the table.
Yeah, in the set, no. It is like an independent data set, like after completing the training process.
Yeah. That's what I mean. It's completely separate data set.
Yeah.
Where you know the truth, and then you apply your model and you compare that with the truth.
Yeah, in this case, I use that method.
And
I want to correct that.
Okay, and that's what we saw in the table. Then I stand corrected. I haven't said anything about.
Okay.
Well done.
Okay, thank you.
All right, we have a couple comments in the Q&A regarding SCG. So I thought I'd share my part of my opening presentation, which we never got to do. But so for those of you who are interested in, and we have many committees at SCG. But I listed some committees that you may be interested in. The top one is machine learning committee. So this is a great place for those of us here if we're interested, and I bring this up because there's a couple comments. First one, will SCG plan to establish some technical standards regarding machine learning application in geoscience? Well, I think we have the tools to do that. So we have the machine learning committee and also a technical standards committee. So I think there's probably a high interest right now just because of exactly what is listed in the Q&A. This person suggests SCG should focus on the practical application and promotion of machine learning application in geoscience, because currently there are so many research papers which test different machine learning algorithms. But how should we use this robust technology? There's no guideline, no industrial standards. So when we use it, everyone uses it in a different way. So we have some of the committees. I know our technical standards committee is pretty active. So I think between the two committees, machine learning and our technical standards, I'm willing to bet that they're probably actively looking at some of these ideas on what can be done. So if you're interested in any of these committees, being involved with SCG, just message me.
So actually, this is which you said is very topical. You said that I think there are too many research papers, and I think people want to see more practical application. And I think some of it is coming up. I mean, we've seen examples. It would be nice to see examples from industry as well. I mean, because I think especially in the areas that are kind of high demanding and very kind of business driven, like, seismic processing, interpretation, there's a lot of progress. So it would be great if SEG kind of leads that. Difficult to share because of various restrictions, but I think people would want to see how things get improved via various methods. That would be brilliant if that's something like that globally gets organized.
Alfonso, you have a question in the Q&A, but if you want.
Okay, thank you very much. So this question, I rather this question to Mr. Paul. So I plan to head a new project for tracking in my country, in Algeria. So my question, for the problem of for tracking using deep learning, is it working in complex areas? It means the structure really complex or no? Or not depending to the complexity area. For example, in Algeria, because in the north and in the south, in the north areas are more complex than the north. So they are stable in the south, and the north areas are very complex. So we can, the deep learning, is it working in complex area or no?
The answer is yes, it works. You should not apply the out-of-the-box trained machine learning model to very complex data sets, because then these models have been trained on rather simplistic faults, so they recognize the faults with a nice throw. But if it becomes more complex, then the results will be disappointing. But the newest workflows that have been introduced and also are supported in commercial packages nowadays allow you to actually retrain or further train these models with input taken from the interpreter. So what the interpreter does, he interprets a number of sections with fault sticks, and then the model is given new examples based on these interpretations. And then the new model, which has been trained on these extra interpretations, will then be recognizing also these more complex fault systems. And that works quite well.
Okay.
But it requires some input from the interpreter to do an initial interpretation.
Thank you very much, Mr.
You're welcome.
The first question about outliers, they should be dealt with before you run machine learning on your data set. This is regardless of machine learning algorithm. I'm not sure if that's a question or a statement.
Yeah, it is indeed wise to remove outliers. So if you are working with log data, then typically you would really take care of getting rid of the spikes and then making sure that everything is scaled properly and harmonized. That's a lot of work, but you need to do that in order to get a training set that is really worth testing. If you have anomalies in there, then machine learning models are not very good in picking up these or tracking these anomalies.
Okay.
So yes, you do have to do that.
All right. So the next question, you mentioned data augmentation, which many researchers applied in their works, even on the synthetic data. So I am interested in what is better to apply the data augmentation on, synthetic data or generate more?
I think you can do it on both. It depends really on what kind of models you can create, what kind of examples. And by increasing the examples, the number of examples through data augmentation, you get more examples to feed into the model, and that is better because of this overfitting problem. So you can do it both for real data, with interpreted data, or you have simulated data and you only have a few of these. Then you can use data augmentation to get more examples. So it can be done for both.
Thanks. I guess the last question in the Q&A, there cannot be standards on machine learning. It's like asking standards for math and geophysics. There could be guidelines or tips for better use or size or dimension of the data sets, etc., but not standards. And maybe that's what the two committees I talked about previously are already discussing, that this is something that you can't really standardize just yet, I guess. Thoughts?
There is one question in the chat. Is it possible to learn how to use some of the AI like seminar or program? I know there is machine learning videos online that are free on how each machine learning algorithm work. They give some example and programming, but it's not about geoscience. I'm not sure there is in geoscience.
Probably there are companies that do some training on maybe some of the algorithms that they use or have developed. I think SEG has some courses, machine learning. I know we have at least one.
We, from DGB Earth Sciences, we are the developers of OpenDetect, and OpenDetect has a machine learning solution. And we give regular webinars, and all these webinars that we have given in the past are stored on our YouTube channel. These are about machine learning, but also on other applications in OpenDetect. So you can find this back on our website or on our YouTube channel.
Thank you. Can the links be posted? I think a Google search on YouTube would probably be a good place to start. Let me see if I can find the SEG Continue Education. I will also mention that SEG has what we call SEG Live. It's a bunch of different webinars, and anything that's done online, whether it's a course, you can find it at SEG Live. And you go to the homepage, come over to events, go down to SEG Live, and any webinar that we've ever done, you can view past recordings of webinars, other events, panels. I believe we have some courses listed there. SEG Live is for anything that's done virtually. So that would be another place to start. SEG has a YouTube channel. All of the webinars that I've ever done for any of my groups that I'm responsible for, including the Eurasia Regional Advisory Committee that organized this event, are located on the SEG YouTube channel. So there's probably a lot of information out there. Creating like a database of resources would be maybe a good place to start.
Yeah, maybe I don't want to make this too commercial, but we also provide free data sets on which you can actually use our machine learning solution, and there's free training manuals which you can use with workflows that are given in or in YouTube, and step-by-step approaches if you want to learn how to do things in our machine learning solution, and it is also possible. It's all for free.
Thank you, Paul.
I know Paul had a question about FIDAN and UVIA, about using both unsupervised and supervised data algorithm. FIDAN doesn't know the answer, and I think UVIA had to attend another meeting or class, I guess. I will make sure that they write to you, Paul, to give you the answer.
Hi,
it looks like
actually, I wanted to comment about this. But I'm not very much familiar for the K-mean that it was not supervised, and the decision tree and random form was supervised. But apparently, if it was not supervised method K-mean, I mean, that's why we had the poor data correlation. Maybe this was a good try to understand which type of the method may work well with our data. So that is the end of the comment.
Okay, thanks.
Thank you.
Is it possible to create a website containing data for AI community? I guess this is an interesting topic. A lot of people have different opinions on this. I'm going to say it. GitHub. Now, some people really, really enjoy it, and others do not so much. Anyone have any feelings on GitHub?
GitHub is a fantastic resource if you are into research. There's enormous amount of code there and examples where you can really get a start if you want to get into to research. But obviously, you need to be able to understand that code, and that is often the main problem. So if you are a PhD or a research guy and you want to look for the latest technologies in deep learning, then GitHub is where you should go. If you are a commercial or operational user, then you simply don't have time to actually dig into it and understand it and apply it to your own technology. So it's a good starting point for research, and then you can modify whatever the guy before you did. But yeah, if you want to work commercially, then I think you better stick to a commercial application.
And nowadays in research, there is open data. They are trying journals and everything they ask for you to share the raw data. So you might also find this type of data like that. I do not remember the names of the sites. However, there is now, yeah. Well, I'm not sure it's about wells and because usually these are confidential data. So.
Yeah, I believe SEG does that as well for publications, at least Geophysics. Some of our machine learning articles and stuff, they provide the data, the raw data, I guess, to go with it, so that some of the algorithms can be tested, I believe. There are many.
Laurie, you mentioned the difference between SOM, Cohen, and unsupervised vector quantizers.
Yes.
I have a slide in which I explain the workings of an unsupervised vector quantizer. So that it basically explains how the algorithm works. And I also have a slide on how a multi-layer perceptron artificial neural networks actually get to its results, or what is happening inside the neural network. If there's interest, I could show these two slides and explain the way I look at these things, if that's of interest.
We have time whenever you're ready.
Okay, so this is an unsupervised vector quantizer, and that is very similar to k-means clustering, and it's also similar to a coherent network, and a coherent network is a self-organizing map. Suppose I have a mapped horizon and I want to do a waveform segmentation, and I take two amplitudes, one at the horizon itself and one below, and I'm giving that to an unsupervised vector quantizer, and I'm randomly picking positions on my horizons to extract these two amplitudes. Yeah, so then I have on the x-axis my amplitude 1 and on my y-axis amplitude 2, and these are the green dots. So I've extracted these different attributes, and I'm plotting them here as these green dots. And what I want to do now is I want to cluster this into 3 different clusters. And these 3, the number 3 is my user-defined number. So I'm telling the system, please cluster this into 3 clusters. And what the algorithm does, it generates 3 random positions in this space. So it creates a vector for me which is this one, P1, another one, P2, and P3. These are randomly picked in this space. And now in this cluster finding method, I'm going to train my network to find these cluster centers. And the way to do that is that I'm picking at random an example from my green positions from the training set. So if I pick this position here, then I'm going to measure the distance between this position. So between this position and each of these factors. And that is just the Euclidean distance that I'm computing. Now this one is closest to P3. So this one is declared the winner, and I'm moving my cluster then. I'm updating this factor a little bit into the direction of the input that I've given. Then I'm picking another random example, now this one, and now P1 is the winner, and I'm moving this cluster, changing the cluster or this P1 factor a little bit such that it moves in the direction of my input example. And if I'm doing that over and over again, then eventually these cluster factors will move into the center of the data, the cluster centers. And then I have a trained network, the trained unsupervised vector quantizer. And once I have a trained network, then I can give it any combination of input 1, input 2. So I can apply it to the entire horizon. I take the 2 attributes at the horizon and the one below. And then what I'm doing is I'm comparing again, where does this particular input falls? If it is nearest to my cluster center C3, it will be classified as a 3. And I also measure the distance between that input and my cluster center, and that will give me a confidence, a match. If the thing is exactly at the same position as the cluster center, then the match is a 1. And if it is as far away in this space from the cluster center as is possible, then the match is 0. So in my application, I will get 2 outputs, the winning segment and the match. Now, this is an unsupervised vector quantizer, and that is basically the same algorithm as a k-means clustering. A coherent network is slightly different in that it not only updates the winning factor, but also the one that is second. So it updates 2 factors at the same time. And that has the effect that there is an organization in the factors. So that is beneficial, because when I'm going to apply this coherent map to my data, then I want to see clusters which are nicely organized next to each other. Because when I apply a colors bar to these cluster centers, then I would like to see the results as gradually changing colors and not just a psychedelic color scheme, which is very difficult to look at. So what we do in our unsupervised vector quantizer is after we've done the training, which is only updating the winning factor and not the winning and its nearest the second one, we also organize the cluster centers, and then you get basically the same as a coherent map, and that's how these things work. And then I would like to explain the multi-layer perceptron, and this is what we nowadays call a shallow neural network. This is what we did since the 1990s, and which is still very useful in many applications. Basically, what is happening here is that we have an input layer that is fully connected to a second layer. This is the hidden layer, and then we have an output layer, so 3 layers. If I have something going into this node here, then it is multiplied with a weight and given to the next node in the hidden layer. So this node in the hidden layer gets all the information from all these input nodes multiplied with a weight. So the sum of the weights times the input is going into this hidden layer. Here in this hidden layer, we're passing it through some kind of nonlinear function. So the actual nonlinearity of the neural network happens in this hidden layer. This is the perceptron equivalent. That's the mathematical equivalent of a biological neuron. So this node gets all this information from the input multiplied with all these weights, and then it passes through this nonlinear function. And again, we apply some kind of weight to give it to the last node, and that's our output. Now, when we train such a network, we are always knowing the answer, because a training set, and that's why it's called supervised learning, has an input and a known output. And when we train this, then we are comparing what the network actually produces versus what it should be. And that is an error. That error is back propagated through the network to update these weights. Now, and what does that mean? Suppose we have a neural network with just 2 input nodes. So we have 2 variables to go in the network, and we have 3 nodes in the hidden layer. And we only have 1 output. For example, we have a number of wells in which we have 2 seismic samples, 2 amplitudes, and we want to predict the porosity at the well location, the porosity at the reservoir level. And if we plot this in a plot, then we have on the one hand the amplitude 1, and on the other amplitude 2, and on the y-axis we have porosity. So basically what we have a number of wells where we know exactly this is the porosity that we want to have, and what we are trying to find is the optimal surface through all these points, so that once we have this surface, we can give it any combination of amplitude 1, amplitude 2, and the network will then predict exactly the porosity that we want. Yeah. Now, what is happening in the neural network when we do the training is we have amplitude 1, amplitude 2 going into the network, and in the hidden layer, we are continuously updating these weights, and that is equivalent to stretching and squeezing these nonlinear functions, these sigmoidal shape functions, in such a way that if we add these 3 sigmoidal shape functions together, we get the best fitting surface for all the points that we have in our data set. And once we have found that surface, we have a trained neural network, and we can apply it, and we always get a result, because we then give amplitude 1, amplitude 2 at a certain seismic location, and it predicts porosity for us. That is the way I look at these things. Any questions?
For tracking problem using the deep learning, do you think that using the seismic attribute like the variance, the counts, rather than seismic data will give better results or no?
In these type of neural networks, the multi-layer perceptron, we always fed these with attributes. That was the standard practice. We have used this technology, for instance, to create chimney cubes, so to see vertical disturbed zones in the seismic. And these chimneys, they can then be related back to fluid migration paths. Where did the gas or the oil come from? Where's the source rock? How did it migrate into a trap? And did it leak from the trap or not? And that was purely done with attributes. So you trained the network on locations that were picked by a user, like this is a chimney and this is not a chimney. And then at each of these locations, you picked 20 different attributes which had the potential to distinguish between these two classes. Is it a chimney or is it not a chimney? And then you fed these into the neural network, and together the network combined all this information in such a way that it found the optimal way to separate these two classes. And that's what we have been doing for more than 20 years, 25 years. Nowadays, if you look at deep learning, you're basically going away from these attributes, because the convolutional neural networks, they actually extract the features, the attributes, directly from the seismic input cube. So you rather give a cube of seismic data that can be a 2D image, like 128 by 128 samples, or it can be a block of seismic data, also 128 by 128 by 128, which is the typical size nowadays. And then you pass that through a convolutional neural network, and in the convolutional step, that information from the seismic is transformed into a feature map. And the feature map is basically the equivalent of the attributes that we have supplied to the artificial neural networks in the shallow neural networks. So we are stepping away if we're going in the deep learning mode and just let the algorithm extract the features rather than we do that upfront. That is a difference. You don't have to do that, but it's what is happening in practice.
But in the deep learning problem, sometimes the overfitting problem is a real problem.
Absolutely, yeah, and that is why you always in any deep learning or artificial neural networks type of work, you always have to really look carefully at your training sets, on your validation sets, on your procedures, and you really have to try to capture the problem that you're trying to solve. And the real key question always is, do I have a representative data set? And if I don't have that, then whatever comes out, and that is the danger of these techniques, they always produce something, and that something is only valid, or it only brings value to me if I have done the entire procedure correctly. Also, if I have validated it against blind test data, and I'm confident that it did a good prediction at these blind test locations. So now I'm confident that this indeed adds value. So it's you really have to be careful, and you have to be aware that you can produce nonsensical results if you're not careful. But if you're doing it properly, then it really can add value.
So smoothing the seismic data before deep learning can avoid the problem overfitting or no?
It completely depends on the problem, whether you want to do pre-processing of the data and what kind of pre-processing you want to do. If we go back to the chimney cube type of application, what we're trying to see in the chimney cube is basically noise trails, vertical noise trails. So if we would smooth that out before we do the attribute extraction and the neural network training, then we have lost a lot of the information that we actually want to see. So in that case, it's not a good idea. But if you are doing, for instance, a fault prediction, then it makes sense to remove noise and to sharpen the edges with an edge preserved smoothing filter, because then you get better results.
So in case of noisy data, the deep learning is difficult or is it impossible? Are you agree with me?
It is absolutely possible, and it is definitely where we will see more applications in the future. But it's already here with really valuable applications. It is definitely not impossible, but it is something you have to be careful with. You should not abuse it. You should use it carefully.
Thank you very much. Thank you, Mr. Paul.
You're welcome.
All right. Yes. Thank you very much, Paul. I think everyone enjoyed it. In fact, comment in the Q&A says that your explanation of the multi-layer perceptrons is the best they've ever seen. The geometric view helped a lot. So thank you. Last question for the day probably will be, will machine learning technology replace the conventional geoscience workflow, just like the autopilot technology replaced the driver?
Is that a kind of general philosophical question? It's a general.
Yeah, I think it was a general philosophic question. Yeah.
I don't know if they would, what we're seeing is, I'm not a practitioner, but what we're seeing here slowly in other companies is slow encroachment on the machine learning methods onto kind of human space and general interpretation. It's happening. It is, exactly people will interpret and make business decisions is not very clear. And I think there is some movements in that space, but in 10 years from now, I think there's going to be a very different kind of workflows of how to arrive to specific decisions based on the data interpretation. We used to do a lot of manual work, and now we just need to do a lot more analytics. Maybe even analytics will be done by AI. So I don't think that, I don't know what others think, but yeah, it will change a lot.
I fully agree with that. I think we are just in the onset of this new technology, which is getting more and more into our industry. Also, it's being accepted more and more that this is valuable information and valuable technology. But we always will need geoscientists who either to create the training sets and to understand the problems and to convert these into workflows that are driven by machine learning models, but also in the interpretation afterwards. I don't think there will ever be a solution where you just press a few buttons and you get the results without fully understanding that. It's way too complex for that to capture all that information.
Thank you, everybody, for attending. Thank you, Paul, for sharing your additional slides. Nazim, if you would like to say some last words.
Unfortunately, I wasn't able to just listen probably with many interesting talks. I think they will be recorded for others, I guess, so people can listen to them, the ones who attended. And I'm really thankful for people who participated. It's the first time we organized this event from the Eurasian chapter. I think we did around a couple of years ago. We had, for COVID, we had face-to-face workshops. So that's the second workshop, and I hope you really liked it. And this is an area we'd like to continue helping the community, especially, I see a lot of people from, other parts of the world here participating. Obviously we have participation from China to US, and that's really cool that it's very kind of global. Thank you very much. And I do see there's a hand. Somebody wants to say something. So
thank you very much for everybody for organizing this work. To just organize in the next year or workshop with physical presence, not the face-to-face, the physical presence.
Okay, thank you. Yeah, virtual workshops are very good, but face-to-face is a little bit better. So, but it's kind of nice to have a global presence at an event as well. So, Nazim, thank you. Izat, the entire technical committee who worked very hard to put this together and organize it. Thank you for all the presenters for presenting your research and your work. And I hope you enjoyed the event.
And thank you too for helping to run all of it.
Thank you too. Yes.
Great. It's great.
Yeah, well done, Laurie.
Thank you.
Thank you, Laurie.
Have a great day and a nice weekend. Oh.
Well, I was trying to. There is an option to applaud, but I don't know where it is, so I'm gonna.
I don't know how to applaud either. All right. Have a great weekend.
Thanks, everybody.
You too.
Bye-bye.
Bye. Bye-bye.
Bye.
Bye.